This episode is brought to you by Brilliant. For centuries, the backbone of agriculture was the horse-drawn implement. This clever horsepower tool, for example, is a horse-drawn mowing machine used for cutting hay. The cutting apparatus consists of sharp, triangular teeth that form a cutting bar and the reciprocating scythe. This particular variant, built by Watkins and Bryson, used a shaft that transmitted power from the machine's wheels to the gear train that drives the cutting mechanism. What made this machine particularly noteworthy could be found within its patent. Issued in 1861, Watkins and Bryson described the first modern conceptualization of a driveshaft. Early automobiles predominantly used chain drives due to their simplicity, reliability, and manufacturing efficiency. This system offered design flexibility, allowing for various engines and chassis configurations, and was easier to produce with the manufacturing capabilities of the time. Chain drives were also efficient in power transmission and benefited from existing familiarity and experience in other industries like bicycles and industrial machinery. However, by the end of the century, the move to more enclosed and durable gear-driven systems occurred, addressing the limitations of chain drives such as exposure to elements and maintenance demands. The 1901 Autocar, designed by Lewis S. Clarke of the Autocar Company, is considered the first shaft-driven automobile in the United States. The Autocar featured a water-cooled, shaft-driven, two-cylinder, horizontally opposed engine and was promoted as a revolution in automotive design at the time. Autocar had established the general rear-end layout known today with their earlier models. The engine was coupled to a then novel transmission known as a sliding gear transmission, which used a combination of gears that could be engaged or set to freewheel along with a dog clutch to produce 3 ratios. The output of the transmission was flexibly coupled to an assembly known as a torque tube that housed a driveshaft and a bevel gear assembly with an integrated gear differential that routed power through axial shafts to the wheels. Because the entire rear driveline moved independently of the engine-transmission combination on the rear suspension, a flexible coupling was needed to deal with both angular differences and changes in distances as the rear suspension articulated. Autocar used a flexible coupler known as a universal joint, specifically a variation known as a pot-type universal joint. This configuration used a pot-shaped housing that allowed it to swivel and slide as it turns, though this joint's simplicity came at the cost of high friction and wear. Within a year, a more robust driveshaft configuration would be developed for the Dutch Spyker 60 HP, the world's first gas-powered four-wheel drive race car. Known as the car of 3 firsts for its additional use of the first 6-cylinder engine and four-wheel braking, it pioneered the use of a Cardan universal joint in combination with a slip yoke within the driveline. The Cardan universal joint traces its origins back to the work of Gerolamo Cardano, an Italian mathematician, physicist, and philosopher in the 16th century. Although Cardano did not invent the joint, he is credited with the widespread introduction of the concept, which was initially explored for applications in geometry and astronomy. A Cardan universal joint consists of 2 yokes at right angles to each other, connected by a cross-shaped intermediate journal, allowing the transfer of rotary motion between 2 shafts that are not in direct line with each other. It allowed for the efficient transmission of power through different angles, accommodating the relative movement between components. In Cardan universal joints, the rolling surface minimizes the surface-to-surface resistance that typically occurs in pot-type universal joints, where the contact surfaces are primarily sliding. These early joints used bronze bushings to further cut down friction and wear. By the 1920s, bronze bushings would be replaced by needle roller bearings that retained their own lubrication and were capable of being regularly lubricated via a grease fitting, leading to a dramatic increase in durability. However, unlike pot-type universal joints, Cardan universal joints did not provide any axial movement. To accommodate for this, a slip yoke mechanism is incorporated into the driveline assembly, allowing it to lengthen or contract as the rear suspension moves. Slip yokes consist of a splined shaft that allows one part of the driveline assembly to slide into another. Much like the Cardan joint, slip yokes can also retain their own lubrication and be regularly lubricated. Despite the improvements Cardan universal joints brought to driveline design, they possess several limitations that can lead to vibrations, increased friction, and excessive wear. Cardan joints exhibit non-uniform rotational speeds when the input and output shafts are at an angle, resulting in non-constant angular velocity transmission. This velocity variation introduces torsional vibrations and cyclic loading, which can lead to premature failure of components. Additionally, the sliding action at the contact points of the joint creates friction that dramatically increases with misalignment angle and operating speed, leading to energy loss and potential overheating. The clearance between the bearing and journals necessary for assembly and lubrication can also cause backlash and excessive wear over time, compromising the joint's efficiency and lifespan. Throughout the 1920s, several design variations have been developed to overcome the limitations of Cardan universal joints. One design called the ball and trunnion universal joint uses a T-shaped shaft that is enclosed within the body of the joint. The trunnion ends are each equipped with a ball mounted on needle bearings, which can move freely in grooves within the joint housing. A compensating spring is used to keep the joint in a centered neutral position. In this design, variations in length are permitted by the longitudinal movement of the balls in the body grooves, while angular displacement is allowed by outward movement of the balls on the trunnion pins. The entire assembly is enclosed within a dust boot to retain lubrication while keeping contaminants out of the contact surfaces. Ball and trunnion universal joints superseded the angle misalignment capabilities of Cardan joints, allowing for up to 25 degrees of movement, and its integrated slip characteristics made it ideal for use in tight spaces. However, the torque capacity of ball and trunnion universal joints, as well as its vulnerability to contamination, limited its application. The late 1920s also saw the introduction of double Cardan shafts as a solution to the limitation of single Cardan universal joints. In this configuration, two universal joints are connected by an intermediate shaft, with the second joint positioned in relation to the first joint to cancel out the varying angular velocity. For this configuration to work effectively, the driving shaft and the driven shaft must be at equal angles with respect to the intermediate shaft, although they don't necessarily have to be in the same plane, and the two universal joints must be 90 degrees out of phase with each other. This intermediate shaft, which is also known as a propeller shaft, or informally the driveshaft, can easily integrate a slip yoke mechanism along its body for axial movement. The double Cardan shaft driveline configuration quickly became a popular choice for rear-wheel drive vehicles due to its flexibility, manufacturability, ruggedness, and torque and angular capacity. It became a popular choice for the Hotchkiss drive, one of the most popular rear-end configurations of the time. It was also easy to maintain and service, requiring only periodic lubrication. It did, however, require careful alignment of components in order for the phase cancellation to work. Under improper alignment, the rotating shafts will experience oscillating moments that tend to bend the shaft in a direction perpendicular to the plane in which they lie. This causes a phenomenon known as launch shudder in rear-wheel drive vehicles, as well as overall vibration and premature component failure. Towards the end of the 1920s, a new class of universal joint was introduced called the constant velocity or CV joint. CV joints were developed initially to address the limitations of Cardan joints in front-wheel drive vehicles. In a front-wheel drive layout, the transmission contains the final drive system in a combined unit called a transaxle that directly drives the wheels. In four-wheel drive and all-wheel drive vehicles, this front drive system alternatively may be a standalone differential driven by a transfer case or a center differential. The drive axles or half shafts that transmit this power must accommodate significant suspension movement and steering angles, which would cause excessive vibration and wear if traditional universal joints were used. The tractor joint was one of the first constant velocity joints to be used in a production vehicle. It was invented in the early 1920s by French engineer Jean-Albert Grégoire for the front-wheel drive 1926 tractor. The joint consists of four main components, two forks and two semi-spherical sliding pieces. The male swivel has a tongue that fits into the groove of the female swivel, creating a floating connection. Each fork jaw engages a circular groove on the corresponding swivel, and when the input and output shafts are at an angle, the driving swivel accelerates and decelerates during rotation. However, since the tongue and groove joint between the swivels is a quarter of a revolution out of phase with the fork jaw, the speed variation of the driven swivel and output fork counteract the speed variation of the input components. This cancellation of speed fluctuations ensures that the output speed matches the input speed, resulting in constant velocity rotation. In effect, the tractor joint behaves as two Cardan joints coupled together. While the tractor joint did offer smoother power transfer, its high friction sliding action and bulky floating components made it an impractical solution. The first practical CV joint design was the Zeppa joint, and it would become one of the most popular CV joint variants used today. Invented by Ford engineer Alfred H. Zeppa in 1926, this innovative design is based on ball bearings in which the balls furnish the only points of driving contact between the two halves of the coupling. A Zeppa CV joint consists of a star-shaped inner race, several ball bearings, a bearing cage, an outer race or housing, and a rubber boot. The inner race is splined into the driving axle shaft, while the outer race is a spherical housing that is an integral part of the outer driven shaft. The balls and ball cage are fitted between the two races, and the close spherical fit between the three main components support the driving shaft. The movement of the balls is controlled by the ball cage, positioning the balls in a plane at right angles to the two shafts when the shafts are in the same line. As the joint articulates, the balls are positioned to one half of the angular movement of the driven shaft. In practice, the vast majority of CV half shafts contain two CV joints to accommodate for the extreme movement experienced by the front wheels. Because Zeppa joints offer limited axial movement but high angular articulation in a compact package, they're best suited for the outboard wheel side of the half shaft, while the inboard transaxial side joint provides more axial movement with less angular articulation. While a Zeppa joint can be used on the inboard side, a less costly CV joint called a tripod joint is commonly used. Developed by engineer Michel Lorraine of Glanzer Spyker in the 1960s, tripod joints have a three-pointed yoke attached to the driven shaft, with barrel-shaped roller bearings at each end. These bearings fit into a cup with three matching grooves, which is mounted to the transaxle. The simple design allows for axial plunge movement of the shaft along with some angular movement. A typical tripod joint can accommodate up to 60 millimeters of plunge travel and about 25 degrees of angular articulation. Despite their capabilities, both Zeppa and tripod joints are highly vulnerable to contaminants and rely on a flexible rubber or thermoplastic dust boot to retain the lubricating grease within the joint and prevent contaminants from entering. These boots are prone to tearing, cracking, or degrading over time due to exposure to road debris, heat, and the constant flexing motion of the joint. Once the boot fails, the grease can escape, leading to accelerated wear of the joint's internal components. Because of the precise dimensions and surface finishes needed for these components to function reliably, boot failure can quickly lead to costly joint failure. During World War II, an alternative ball bearing-based CV joint was developed by Bendix, known as the Bendix-Weiss joint. The Bendix-Weiss joint used steel balls to transmit power at an angle, but employed integrated yokes as part of the shafts. The yokes contain long grooved races for the steel balls, permitting them to move back and forth as the drive angle of the shaft changes. They typically use 4 balls mounted between the 2 yokes with a 5th ball mounted in the center to lock the 4 outer balls in place. The center ball is held in place with a pin, and when the joint is assembled, the steel balls form a tight fit between the inner and outer shafts. This tight fit is necessary since there is no cage to hold the balls, and movement is controlled by friction between the connecting parts. While this design is simpler to produce, it is more sensitive to manufacturing accuracy, wear, and contamination when compared to Zeppa joints. It is also less serviceable due to the integrated yokes. In the 1960s, several manufacturers such as Volvo and Oldsmobile experimented with using CV joints on their propeller shaft assemblies to facilitate smoother, more refined feeling power transfer on their higher-end rear-wheel drive vehicles and sports cars. This proved to be successful, and by the 1990s, the inclusion of a cushioned CV joint on propeller shafts in cars became common. On both CV half shafts and propeller shafts, a support mechanism known as an intermediate support bearing is required when the axle length exceeds a threshold. These bearing carriers reduce driveline vibrations by shortening the effective length of the axle. This improves stability by minimizing flexing and whipping, and it also increases the lifespan of the CV joint. While CV propeller shafts offer smoother power delivery, they lack the ruggedness and serviceability of traditional Cardan universal joints. One solution that dates back to 1916 to produce ruggedized constant velocity in a universal joint is the double Cardan joint. Double Cardan joints place two Cardan joints back to back in a single unit, eliminating the need to correctly phase two universal joints at the ends of an intermediate shaft. To maintain true constant velocity rotation, double Cardan joints require a centering element that ensures equal angles between the driven and driving shafts. While these joints are extremely rugged, compact, and excel at high articulation angles and torque loads, such as those found on off-road vehicles, the centering device requires additional torque to accelerate the integral components of the joint and can generate some extra vibration at higher speeds. Several more elaborate variants of the double Cardan joint have been devised, such as the Thompson CV joint that uses a scissor positioning mechanism, though their complexity and cost have prevented their mass adoption. While universal joints have seen constant development throughout the 20th century, the shafts they couple have seen little change until the 1980s. Historically, driveshafts have been made from steel, typically a high-strength alloy such as 4340 or 1040. Steel driveshafts offer excellent torque capacity, torsional rigidity, and durability. They are also relatively inexpensive to manufacture and have a well-established production process. However, steel driveshafts are heavy, which can negatively impact vehicle performance, fuel efficiency, and overall weight distribution. In 1985, the first composite driveshaft was developed by the Spyker U-joint division of the Dana Corporation for the Ford Econoline van models. That year, GM would also introduce its first composite driveshaft on the C4 Corvette. Composite driveshafts are typically made from aluminum, carbon fiber, glass fiber, Kevlar, or some combination of these materials. Though more expensive to manufacture, composite driveshafts are significantly lighter than their steel counterparts, often weighing 40 to 60% less. They possess a high strength-to-weight ratio when compared to steel, and despite their lower weight, composite driveshafts offer excellent strength and stiffness, enabling them to handle high torque loads without adding excessive mass to the driveline. Composite materials also have inherent damping properties that help reduce driveline vibrations, are corrosion resistant, and allow for greater design flexibility, enabling engineers to optimize the driveshaft's shape, thickness, and fiber orientation for specific applications. Driveline components and their universal joints have been crucial elements of the automotive industry for over a century, and their importance remains constant even as the industry decides its future with hybrid, electric, and other alternative power sources. Though there has been attempts to eliminate drivelines completely by integrating motors directly into the wheels with hub electric motors, this approach has yet to be proven viable due to major design challenges. As a result, the traditional drivetrain layout relying on driveshafts is likely to remain dominant in the near future. In the world of automotive technology, it's often the little things that make the biggest difference. And when it comes to driveshafts and universal joints, there's more innovation packed into these seemingly simple mechanisms that meet the eye. Creating a robust and dependable power transmission system that can endure road use for over 100,000 miles requires a meticulous understanding of design, testing, data modeling, and analysis. A great way to dive right into mastering your understanding of data modeling is Brilliant.org. Brilliant is where you discover the thrill of learning with thousands of captivating interactive lessons in math, data analysis, programming, and AI designed to unleash your potential and transform you into a confident problem solver. Brilliant is an innovative learning platform that stands out for its use of a first principles approach that enables you to build a solid foundation of understanding. Each lesson is brimming with interactive problem solving exercises, allowing you to actively engage with concepts. This technique has been shown to be 6 times more effective than simply viewing lecture videos. Moreover, all of Brilliant's content is developed by a distinguished team of award winning educators, researchers, and industry experts from prestigious institutions such as MIT, Caltech, Duke, and renowned companies such as Microsoft and Google. Brilliant immerses you in active problem solving from the start because truly learning a concept requires more than just watching and memorizing. You need to experience it. By engaging in hands-on learning, you'll not only build real knowledge on specific topics, but also develop critical thinking skills that make you a better thinker overall. Investing in daily learning is crucial for personal and professional growth, and Brilliant makes it easy and enjoyable. With engaging bite-sized lessons that fit seamlessly into your schedule, you can build genuine knowledge in just minutes a day. Say goodbye to mindless scrolling and hello to more fulfilling ways of spending your free time. A great starting point I highly recommend is Brilliant's Modeling with Multiple Variables course. In this series of lessons, you'll learn to combine information from multiple sources to make great decisions using data modeling and solid analysis techniques based on a strong mathematical foundation. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/newmind or click on the link in the description below. You'll also get 20% off an annual premium subscription.